Okay, welcome back everybody. Sorry for having to record this one. My laptop was totally dead. It had to be reformatted, and I think I broke the record for reformatting and putting everything back on it as quick as possible. Um, so that's the deal. Anyway, so last time we got to kind of our milestone theorem, the thing that we've been working toward. Um, for well, this is kind of like the crowning achievement of the course here, and you'll see why hopefully in the next couple lectures with all the applications I'm going to go over. And this is the residue theorem. Okay, and so this says that if we have a function, it's analytic inside and on some positively oriented simple closed contour, except at finitely many singular points, then necessarily those are isolated singular points. So they can be isolated in this way that I've drawn here in the picture. Okay, and if we have curves here, right, that we can think of as these circles that are isolating those singular points, well, actually I can compute. I can actually compute this contour integral of f over this outer curve as 2 pi I times the sum of the residues at these points. And of course, these residues you could view as coming directly from contour integrals along these circles, c sub I, which is how we proved this, right? So actually the proof of this was essentially all it required was that fact that we had back when we talked about multiply connected domains a couple weeks ago. That was all that was needed, essentially, this Cauchy-Gorsat for multiply connected domains. We applied that, and out of it popped the residue theorem. Okay, and so we did an example of using the residue theorem to compute a contour integral. So in fact, the example we ended with was using the residue theorem to compute the contour integral of this thing. This had two singular points. There they were. Okay, and so all I had to do was compute residues here and here. And then this contour integral is just 2 pi I times the sum of the residues. So we found that the first residue was 2, the second residue was 3. And so this was 2 pi I times 2 plus 3, so 10 times pi I. Now, if this thing had had more singular points inside this curve, then I would have had to compute more and more residues. And so now what I want to do is show an example of how we can actually, if we're careful, sometimes get around computing multiple residues and compute this integral as or from a single residue. But in order to do that, I need to talk about residues at infinity. Okay. Okay, and so this is related to, we talked about the notion of a singular point at infinity, and so a residue at infinity is necessarily related to that. So suppose that our f in question is analytic on C except for finitely many singular points inside C. Interior to positively oriented simple closed contour C. Okay, so our typical picture. Okay, so let's maybe I should have drawn it more symmetric here, but let's say that I have an F, and here's some finitely many singular points. There we go. We'll say that's what they look like. And here is my C. Okay, here's C, positively oriented. All right, there we go. And I have an F that is analytic on the entire plane except at these singular points that are interior to this contour C. Okay. All right. Now, suppose that that r sub 1 is a number that is a real number that's positive, such that C lies entirely inside the circle of radius r sub 1 centered at the origin. Okay, so what would this look like? So maybe r sub 1 is big enough so that this is the case. All right, so my circle lies entirely, or sorry, my contour C lies entirely inside this circle that I've indicated here. Well, then, for instance, right, outside of this circle, right, if this is a circle of radius r sub 1, then, of course, since all the singular points of f are inside this curve C, and this circle is even separating the curve out further, then outside this circle, f is analytic, right? So then f is analytic, right, on the region, well, really on the domain, described by all complex numbers having modulus strictly greater than r sub 1, and say strictly less than infinity, right? So it's the rest of the plane, not including the point at infinity. Okay. And in this case, we say that z equals infinity is an isolated singular point of f. This was the terminology we had. Okay, and so if you believe that we're able to consider this an isolated we're able to consider the point at infinity an isolated singular point, then it stands to reason that we should be able to talk about the residue, right, at z equals infinity in some way that makes sense. So how do I do that? So the idea here is that I define another circle, right? So I define a circle that is inside this region, which means it is a circle that is outside this circle of radius r sub 1. So here I'm going to draw it as a solid line here, or a solid curve here. This is going to be a circle, so let that circle, we'll call this C naught, and we'll say that C naught is the circle that is modulus of z is equal to some r naught, and r naught is clearly greater than r sub 1. So r sub 1 is strictly less than r naught. Okay. And let us give the orientation on C naught to be clockwise. Okay. Okay. Now, why are we giving this the clockwise orientation? Okay, well, imagine yourself here, right, on the interior curve, right? If I'm wanting to think about applying some residue theorem stuff, as I traverse this curve in the positively oriented direction, the singular points of f lie in what direction to me? So here I am, this is me, I'm walking along this curve. All of these singular points are going to lie to my left, right? They're going to be to my left side. Okay, so I'm keeping all my singular points on the left here. Okay, so that's important. So I'm keeping all the singular points on the left. Now, I want to define residue in a way that is consistent with the way that I defined residue for singular points that look like this. Okay, so if I want to do that, I need to talk about a curve that encloses that singular point. Here, that singular point that I'm talking about is the point at infinity, right? You can view the point at infinity as being off, right? So you keep going out the finite plane to the end, right? This point at infinity. Okay, so the point at infinity is that direction, but it's also that direction, that direction, that direction. Okay. All right, and so just like this interior curve is encircling these singular points of f that are inside of it and keeping them on the left, this curve C0 is encircling, right, the point at infinity, and I want to make sure that I orient it in a way that keeps that point at infinity to the left. Well, in order to do that, this orientation needs to be clockwise. So if this is me and I'm moving clockwise around this, then the point at infinity is always to my left, right? If I was moving counterclockwise, it would always be to my right, okay? Which is not how this setup inside is. So I want this to remain consistent, so I have to have this clockwise orientation. Okay, so say that this is our setup now. So now, what is the residue at infinity? So the residue of f at infinity is the following. This is the contour integral over that C0. This is my circle that is encircling, right, the the singular point at infinity. This is defined. Maybe I should say that, so it's not this, it is the thing that I'm about to write here. So the residue of f at infinity is defined by the following. It's 2 pi I times this residue at infinity of f. So the way that we could write this, i.e., of course, the residue at infinity of f, you could think of as being defined by, if this definition is going this way, this is defined as 1 over 2 pi I times that contour integral. Okay. But let's go back to our picture. Right here I have a different contour integral, but I want to involve this original curve C, right? The same curve that I would be using if I was going to use the residue theorem, right, to compute residues here. Okay. And because that's the integral that ultimately that I want to compute when I'm using the residue theorem, right? Well, how do these two relate? Well, we know that our function f is actually analytic everywhere on the plane except at these points that I've indicated, and of course it's point at infinity. And so I could actually continuously deform this curve C0 to this curve C, because f is analytic everywhere in between. So by the principle of deformation, these two integrals would match up, except the orientations are reversed. Right? And so what this means is that, but by principle of deformation, what I get here is that the integral over the original curve C of f of z dz is equal to the integral over minus C0 f of z dz, which is of course minus the integral C0 f of z dz. And so we actually have a definition of the residue in terms of not this different contour integral over another contour, but actually over that curve C that we started out with, i.e., the residue at infinity of f is 1 over 2 pi I, minus 1 over 2 pi I times the integral over C of f of z dz. Or if you prefer the other formula, the integral over C of f of z dz is equal to minus 2 pi I times the residue at infinity of f. However you want to remember this. Okay. Now, it turns out that to compute this residue, right, what is it that we want to do? Well, let's write f as a Lorentz series and do the thing that we always do to compute residues, right? We write the function as a Lorentz series, and then we want to actually pick out the coefficient, right? The -1 coefficient, the coefficient on the negative first power, right, in the Lorentz series expansion. And so let's do that. So let's compute this residue. So since f is analytic, so f is analytic on this domain, right, outside the circle of radius r sub 1, i.e. It has a Lorentz series expansion. So this is the sum from n equals minus infinity to infinity of c sub n times z to the n on this domain. I'm not going to rewrite that. Okay. Where, of course, by Lorentz theorem, the c sub n's can be computed in the usual way as 1 over 2 pi I times the integral over, say, minus c naught f of z dz over z to the n plus 1 here, right? Where n is n is taken to be any integer value, right? So this is n is 0, plus minus 1, plus minus 2, and so on. Okay. All right. But then how do I compute this residue in question? Well, in order to pick out, so here's the residue, right, in question. How do I compute this? Well, so firstly, dealing with the point at infinity, I could replace z by 1 over z. I could replace z by 1 over z here so that I could actually compute, I could actually plug in, right, the point at infinity. But if I do that, in order to actually pick out this minus first term, I would need to multiply the Lorentz series expansion by 1 over z squared. So that's how I would do this. So I replace z by 1 over z and multiply by 1 over z squared. So replacing z by 1 over z and multiplying by 1 over z squared, I get the following. So I get 1 over z squared times f of 1 over z, which is what? Well, in the Lorentz series, this is a sum from n equals minus infinity to infinity of c sub n times 1 over z to the n plus 2, right? Which I can rewrite by shifting index as the sum from n equals minus infinity to infinity of c sub n minus 2 over z to the n. Right? And this is, since I've went from z to 1 over z, and I was here in this region, now I'm in the region modulus of z is, so inverting infinity, that's 0, right? And inverting r sub 1, that's 1 over r sub 1. Okay. All right, and thus c sub minus 1 is, that is the actual power we're looking for here, because this is when n is equal to 1. So when n is equal to 1, I get c sub minus 1 here, and I get 1 over z, which is exactly the term that I want. So this c sub minus 1 is the residue at z equals 0 of 1 over z squared f of 1 over z. And so the way that we can compute this residue here, the residue at infinity is the residue of, or the residue at 0 of this thing, instead of having to think about, this is our way of plugging in infinity here, right? Okay, i.e. the residue at infinity of f of z is equal to minus the residue at z equals 0 of 1 over z squared f of 1 over z. Okay. And so what have we actually shown? So we've actually proven a theorem here. So we have proven the following. So we have a theorem that tells us if a function f is analytic everywhere, in C except for a finite number of singular points, interior to a positively oriented simple closed contour. So interior to a positively oriented simple closed contour C, then an alternative way of computing the contour integral over C of f is 2 pi I times the residue at 0 of 1 over z squared f of 1 over z. This is an alternative to the residue theorem, if you like. The cool thing about this is that this only requires computing a single residue, okay, instead of a sum. Okay, so sometimes this is more efficient to do, okay, when you can actually do it. All right. So let's apply this to the example that we did yesterday. So by the example that we did yesterday, this contour integral of 5z minus 2 over z times z minus 1 was 10 pi I. We had to compute two residues, right? The residue at z equals 0 and the residue at z equals 1. Okay, we found those were 2 and 3, and so we used the residue theorem, and we were happy. Okay, so let's do this for residues at infinity to try to do this with a single residue. Okay, and so let's let our f of z be just like in that example 5z minus 2 over z times z minus 1. Okay, and let c be the circle of radius 2 centered at the origin, described counterclockwise, so it's positively oriented. But note that if we look at 1 over z squared times f of 1 over z, what do I get? All right, what is this? So let's just figure out what this is exactly. Well, this is 5 minus 2z over z times 1 minus z, or this is 5 minus 2z over z times 1 over 1 minus z, which I can write as 5 over z minus 2 times, I can use the geometric sum formula for this thing. So this is 1 plus z squared and so on. Okay. But then the only term here where I'm going to have a z to the minus 1 is the term I get from in the product 5 over z times 1. So this is actually 5 over z plus 3 plus 3z and so on. Okay. All right. Of course, the 3 comes from 5 over z times z minus 2, right? So I'm not implying there's like a nice systematic way of doing that. I was just showing you a few of these. And this is for modulus of z strictly between 0 and 1. Okay. All right. Now, doing that, then my residue at infinity is 5, right? So this contour integral, using this fact here, of 5z minus 2 over z times z minus 1 dz, this is 2 pi I times the residue at 0 of that thing, 1 over z squared, f of 1 over z, but that's 5, right? 5 is the coefficient of 1 over z here. So this is 2 pi I times 5, which is 10 pi I. Hey. That's exactly what we expected it to be, right? If we go back to our example where we used the regular residue theorem yesterday, that's exactly what we got. Okay. So it's kind of neat how the 5 popped directly out of the algebra here, right? You can actually see it. Okay. So that's how that goes. All right. So this gives you an alternative to the residue theorem if, for instance, you wanted to compute this with a single residue. Okay, and this is via these residues at infinity. Okay, so this is a nice tool to have in your toolbox. Okay. So now, for us to go further, it makes sense to actually classify the type of singular point that we are dealing with. Okay, and so the idea here is the following. We already know that there are really, really bad types of singular points, like for instance a branch point, right? So a branch point is something nasty. That was like our first example of something that was not an isolated singular point. So we're already dealing with isolated singular points, and that's part of our assumption when we're wanting to use the residue theorem is that we're dealing with isolated singular points. But even restricting ourselves to isolated singular points, there are types of isolated singular points. There's 3 main types that we're going to talk about. So there are 3 types of isolated singular points. Okay. And the way that we are going to think about these intuitively is that 2 of them we can deal with in a nice way. Now, I shouldn't... Okay, so let me back up for a second. When I say deal with, I'm not implying that like we're stuck and we can't use the residue theorem or something like that. That's not what I mean. I should clarify here and say that 2 of these we will view as having the function has nice behavior near those singular points. Okay, and there's one of these types, which I've mentioned before, where the behavior of the function is a lot crazier and maybe less regular near that type of isolated singular point. So I'll go ahead and tell you the names of these. So we're going to talk about removable singularities. There's the notion of a removable singularity. It actually relates to things that you've actually seen all the way back in Calc 1. Poles, that's another type, okay, of singularity of an isolated singular point. And the last type is essential singularity, which I've mentioned previously. Okay. And so these 2 are nice, and essential singularities are less nice. Okay. But in order to actually discuss any of these, I need to basically characterize them in terms of what the Lorentz series looks like for f near such a point. So how do I classify these? I classify these things by looking at the Lorentz series expansion on the punctured disk in question. So on some annular region, well, particularly the punctured disk here, okay? And so I classify these, so if I'm talking about isolated singular points, z0 of a function f, for which z0 is an isolated singular point, okay? Then if I'm talking about Lorentz series representation, what does that look like? We know we have this part of the Lorentz series representation. That's the power series portion. Okay. And then we have the portion that concerns the negative powers of z minus z naught. Okay. 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 Now, in order to classify which of these occurs at a given singular point, we look at this part, the part involving just the negative powers. This is called the principal part of f at z naught. Okay. Okay. This principal part, of course, like the only thing that changes here are what the coefficients are, right? And so clearly the classification is really going to depend on what these coefficients are. Okay. All right. So there are three cases. Okay. So first case. All of the b sub n's are 0. Okay. In this case, we say that f is a removable singularity. Or f has a removable singularity at that z naught. This means that f has a removable singularity at z naught. Okay. The second case is at least one b sub n is not 0, but all except finitely many of the remaining b sub n are 0. So we have at least one that's guaranteed to be non-zero. The rest of them could be 0 or not, but if any other of them are not 0, there can only be finitely many such terms. Okay, and so the idea is that if you listed out all of these coefficients b sub n that are not 0, you would only have finitely many of those. Okay, this is f has a pole at z naught. And we'll talk a little bit more about terminology here, because when we talk about a pole, we talk about the order of the pole there as well. Okay, and then lastly, we have the case where all b sub n. So we've covered the cases when every single one of them is 0. We've covered the cases when finitely many of them are non-zero, but the rest are 0. So then the last case is all b sub n are non-zero. So looking at the principal part, every single b sub n, every single coefficient is non-zero in this last case. Okay. This is the notion of f as an essential singularity. At z naught. Okay. Okay, so now I want to consider examples that show what's going on here. So let's look at case 1. So case 1. What's an example that illustrates what can happen here? Note that z naught equals 0 is a removable singularity of the function f of z, which is 1 minus cosine z over z squared. Okay. Why? Well, first of all, is this a singular point? What is f of 0? Okay. Well, f of 0 is 1 minus cosine 0 over 0 squared. Okay, so I can't, that's undefined, all right. But notice that if I were to actually write the Lorentz series expansion for f, well, I know what 1 minus cosine z is. That's easy enough. And then, so I'm going to have 1, so this is 1 over z squared times 1 minus cosine z. If I use the Taylor series expansion, or Maclaurin series expansion for cosine z here, what do I have? I have 1 over z squared times 1 minus, and the Maclaurin series for cosine z is 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial, and so on, right? Okay, so I have 1 minus 1, then I have a bunch of minus signs here that flip. And so what do I get here? I get, so 1 minus 1, that cancels, and what I'm left with here after I multiply through by z squared is I have minus minus z squared over z squared times 1 over 2 factorial. So this is 1 over 2 factorial minus z squared over 4 factorial plus z to the 4th over 6 factorial minus z to the 6th over 8 factorial, and so on. All right, so that's what I get here. Okay. Thus, what do we note? F of 0 written like this is undefined at 0, right? So f of 0 is undefined. But what should it be? Right? Looking at this, when I plug in 0 here, all these terms go away. And I have 1 over 2 factorial, which is just 1/2. So note, if I define f of 0 to be 1 over 2 factorial, that is 1/2, then f of z is actually entire. It's actually analytic everywhere. Okay. Because this thing, the reason why I can do that, you might say, well, how can you do this, right, at 0? How does any of this make sense? Because this Lorentz series expansion you're looking at on this punctured plane, right? So you're fine. And so what is, intuitively, what is it that's going on in the case of a removable singularity? Basically what's going on is something like this, where you have a function defined in such a way that technically, right, as it's written, it's not defined at some point, so it has a singularity at that point. So for instance, in this case, 0. Right, so f of 0 is undefined technically. But if you actually look at it a little bit more closely, if you look at its Lorentz series, you will see that out of that pops a suggested value for how you could define this function in order for it to actually be analytic at the point that's supposedly a singularity. Okay? And so it is a singularity. But what you can do is define an extension of that function, right, that has a value that you choose at 0, right? So technically this is like a piecewise function if you like. And it's actually analytic there. And so you have removed the singularity, okay, by doing this definition. So we removed the singularity at z0 equals 0. Okay. We have removed it. But think about, like, this makes perfect sense when you go back to how we actually define these things, right? So going back, the case we're in is when all of these negative power coefficients are 0. But in that case, all those are 0. And so what is f? F is just a power series, right? And so if f is a power series, though, we know that it's analytic, right? It's just that we're considering this Lorentz series business on some, punctured disk or an annular domain. In this case, punctured disk at z0. Okay? And so we can actually extend this power series to the entire disk. It's no longer punctured by looking at this and picking a value for f at z0. Okay, so that's the idea. Okay, so this is one of the nicest things that can happen when you have a singularity, right? So we removed the singularity, and hence it's a removable singularity. Okay. Okay. All right, so let's look at case 2, right? So in case 2, I'm going to say a little bit more about terminology here. Okay. So in case 2, the following is happening here, right? So we have some we have the principal part that has one non-zero term, and so in this case, so for instance, in general, say b sub m is non-zero, right? And this is the largest such non-zero value, right? So in that case, everything that comes after it is 0. Right? That must be true if we're in the case where we have only finitely many non-zero terms, right? So everything else has to be non-zero. Okay, and so in this way, we can write f of z having Lorentz series expansion that consists of the power series part, okay, plus the principal part, right, up to this m, which is the largest, it is our largest index that is not such that b sub m is non-zero. Okay. Now, if you notice, I didn't actually say that any of these are not 0, right? They could be 0. Okay, where b sub m is definitely non-zero. These others are, maybe they're 0, maybe they're not, right? Okay, but if we're in this case, and m is the index of or it's the largest index such that b sub m is non-zero, we say that this z0 is a pole of order m. Okay. A pole, if m equals 1, we say it's a simple pole. Now, you might immediately, the second I say that, you might immediately tie this together with the notion of a root, like a simple root, which is a root with multiplicity 1, right? And that's not a bad idea because it's going to turn out that poles and zeros of functions, or poles and roots, are closely related. Okay, these are actually closely related concepts. Okay, so this is a pole of order m. So this is in general what happens. Now let's look at some specific examples. Okay, so what about a function like this? So let's say let f of z be z squared minus 2z plus 3 over z minus 2. Okay. All right, first things first, when you have a quantity like this, you want to do some algebraic trickery to make this thing look a little bit nicer. So notice that if we factor out a z here, we get z times z minus 2 plus 3. So this actually makes this a lot nicer here to view this as z times z minus 2 plus 3 over z minus 2. Now we're happy. So this is going to be z plus, this is going to be z plus 3 over z minus 2. Right. Okay, and if we want z minus 2 showing up everywhere, then we can write this algebraically as 2 plus z minus 2, right, plus 3 over z minus 2. Why are we doing all these algebraic tricks? Because we want to put this in a very specific form where we have a z minus 2, right, to some power in every term. Okay, and this is on the domain modulus of z minus 2 is between 0 and infinity. Right, so the punctured punctured disk at 2. Okay. All right. So, what can you say about this? Well, since I can write f of z as Lorentz series expansion, where the highest index here is the first power of z minus 2 in the denominator, so it's the minus first power here, right? Then this, so z equals 2 is a simple pole of f. Okay, that is a pole of order 1. Okay. Notice that since this is a pole of order 1, we also have that this coefficient, of course, there, the b sub 1 term there is actually the residue, right? This is the residue at z equals 2 of f of z, which is 3, right? Okay. We didn't need to say anything about that, but that's just nice to notice. Okay, so this is a simple pole or pole of order 1 of f. Okay, let's do another example. Okay. What about f of z? That's 1 over z squared times 1 plus z. Okay. How do I want to write this to make use of my algebra for Taylor series to come up with a Lorentz series here? So here I can write this as 1 over z squared times 1 over what? I need 1 minus z here to use my geometric series formula whenever z is within unit circle. All right, so what is this? This is 1 over z squared times, using geometric sum formula, this is 1 minus z plus z squared minus z cubed, and so on. I'm doing 1 minus z squared here, so this is 1 over z squared minus 1 over z plus 1 minus z plus z squared, and so on. Okay. And of course, this is for Z in punctured unit disk. Okay, but this is the principal part, right? Okay. And for the principal part, what's the highest index here showing up? Uh, um, well, it's the second one, right? It's the second power. Okay, and so F has a pole of order m equals 2 at the origin, z equals 0. Okay. Of course, you can also notice, just for practice, the residue here of F is coefficient on the 1 over z term, which is minus 1. Okay, just for practice. Okay. All right. What else? Let's do another example. Let f of z be sinh z, so hyperbolic sine, over z to the fourth. So you might look at this thing and you have some ideas in your head about just looking at it, what the order of the poles is going to be. Right? But to actually see how this works, of course, I just look at 1 over z to the fourth times the Maclaurin series expansion for sinh z. So this is z plus z cubed over 3 factorial plus z to the fifth over 5 factorial and so on. So 1 over z to the fourth, what does that give me? This gives me 1 over z cubed plus 1 over 3 factorial times 1 over z plus z over 5 factorial and so on. Okay. And so here's the principal part. The pole is a pole of order 3 here. All right, so pole of order 3 at the origin. And the residue at the origin of f is coefficient on the 1 over z term, which is 1 over 3 factorial, or 1/6. Okay. All right. So now, the last case, right? Case 3. So in case 3, you have a Lorentz series expansion where the principal part has every single b sub n is non-zero. Okay, so immediately here's an example. Right, so we saw this specific function already, e to the 1 over z. This is just looking at the Maclaurin series here. This is the sum from, so the Maclaurin series for e to the z, right, just replacing z by 1 over z, is sum from n equals 0 to infinity of 1 over n factorial times 1 over z to the n. Okay. Which, writing this out, this is 1 plus 1 over 1 factorial times 1 over z plus 1 over 2 factorial times 1 over z squared plus 1 over 3 factorial times 1 over z cubed and so on. So the principal part is this one. All right, so here's the principal part. So every single b sub n is non-zero. All right, so b sub n is non-zero for all n. So this has an essential singularity at z equals 0. So this has an essential singularity at z naught equals 0. Okay, so it's definitely not removable. Okay. And it is not a pole because this doesn't stop, right? This principal part continues on and has non-zero coefficients. Okay. So what is kind of the best way of understanding the behavior of this versus poles and removable singularities? So a way of thinking about poles, right, and we're going to see this in some coming theorems, is if I go back for a second and list out here what happens when you have a pole of order n. Notice that if I had a function f like this, right, and let me get myself an extra sheet of paper. So if I had an f described in this way, okay, then well, let me multiply this f by z minus z naught to the n. Right, what happens? Well, I end up with, you know, the same exact thing, except so I've multiplied here by z minus z naught to the m, so I would end up with a sum from n equals 0 to infinity of a sub n z minus z naught to the n plus m here, right, plus b sub 1 times z minus z naught to the m minus 1, plus b sub 2 times z minus z naught to the m minus 2, all the way up to b sub m, which would be a constant term here, right? And so this has as its principal part just 0, right? This has a removable singularity, right? Or is actually just defined by a power series here, right? And so there is a relationship between poles and removable singularities in that I can actually take my function here and multiply by this thing here. And we'll talk more about this. Like I said, there's some theorems coming up that will kind of tie all this stuff together. But I can actually turn something with a pole of some order into something that is actually describable in terms of a power series, right? And so maybe you're like, well, why would I do that? And you're still changing the function. So, you know, what is that? What are you trying to say here? So what I'm trying to say, though, is that imagine trying to do something similar to something with an essential singularity. Right? You can't do it, right? Because no matter what z minus z naught to the m you multiply by, you're still going to have an infinitely long principal part that has infinitely many non-zero coefficients. Okay, and so actually, you're not only are you not going to be able to do that, to turn it into something that's power series, it's not even going to help, right? You're still going to have infinitely many of those terms in the principal part that are non-zero. Okay, one of the best ways to see what it is that's going on is called Picard's theorem. Okay, so one fun fact that illustrates the craziness of essential singularities is called Picard's theorem. Or the Picard theorem. So I'm going to list two versions of it. One is a weaker version that has nothing to do with essential singularities, at least on the surface, and another one that does. So, so two related facts. Little Picard. So what is the Little Picard theorem? The Little Picard theorem answers a question that actually This came up yesterday in yesterday's office hours. Kind of questions about what sorts of values analytic functions were allowed to attain on some domain. Okay, it was a question of basically the range of an analytic function and if there's any kind of restrictions on what that range can be. Because if you ask a similar question, right, like if I tell you, say that I have a function that is, say, differentiable on some given domain in the reals, right? So a real valued function, right? So if we're talking about a real valued function, and I ask you, well, what is its possible range? The answer is basically anything. Okay, so if I ask you, if I ask you, like, you have a function defined on like 0, 1, and we'll say open, right? 0, 1, open. Like, what are the possible values for the range of that function? I mean, it's pretty much anything. It's pretty much free. You're completely free there, but it's not really the case here for some function that's entire and non-constant of a complex variable. So, for the reals, if you have a function that's differentiable, say everywhere, what is its range allowed to be? Lots of answers, but that's not the case for complex valued functions. So, if f is an entire function and f is non-constant, so it takes more than one value, okay, then the set of values f of z assumes is either the whole complex plane or the whole complex plane minus a point. Minus a single point. Okay. Why do we have to include minus a single point? Right, why is that a possible exception? Quick example. You might have realized it by now. E to the z. Right? E to the z assumes every value in C except 0. Okay. So e to the z is entire, and it's non-constant. And it assumes every single value in the complex plane except z equals 0. Okay, so this is your canonical example of why you have to include this possibility that it misses a single point. But this is it. This is the only this is the only option. Okay, it either hits everything in the whole complex plane, or it hits the whole complex plane minus a single point. Okay, so that's neat. But we also have what is called like greater Picard or big Picard or just Picard's theorem, which has to do with essential singularities, and it tells you something about the craziness of these things. And so we have the Picard theorem. Picard's theorem. What does it say? So there's a couple of statements of this. I'm just going to state it in the way that it's mentioned in the textbook. It's not actually stated as a theorem that is written in bold in the textbook. It's just written in the text in italics, but you can look up various statements of this thing. And this is in each neighborhood. So in each neighborhood of an essential singular point, okay, a function assumes every finite value in C, with one possible exception, infinitely many times. Think about that for a second. In any neighborhood of an essential singular point, a function assumes every complex number value possible, except for it might miss a single point, okay, infinitely many times. Let's go back to our example and see how this relates to Picard's theorem. So we had our example e to the 1 over z, right? So f of z is e to the 1 over z. E to the 1 over z had an essential singularity at z equals 0. Okay. That means pick any neighborhood on z equals 0. So here's z equals 0 here. Here's singularity. Pick any neighborhood you want. Right? There you go. There's one. In that neighborhood, e to the 1 over z assumes every possible complex value, with one potential exception, infinitely many times. Okay. What is the exception? Turns out that 0 is the exception. Turns out e to the 1 over z is never equal to 0. So 0 is the exception. So pick any other complex value. E to the 1 over z assumes that complex value infinitely many times in that neighborhood. Okay. All right, so that's a neat little thing. Again, this is another crazy thing that doesn't really happen in real analysis, right? This is totally different. Okay. All right. And so now we're almost ready to move on and apply this stuff. But this should give us some sense that essential singularities are, well, they're nastier, right? They're harder to deal with. The behavior of the function is much more erratic, right? By Picard's theorem, in any neighborhood of an essential singular point, that function is going crazy, right? It can assume it assumes every complex value with one possible exception infinitely many times in any neighborhood. So it is just going absolutely nuts, right? Okay. So what that means is that essential singularities are things that we hope to not be having to deal with too often. And so hopefully we're dealing with singularity that is at worst a pole of some order. Okay. And so that is our idea here. And so idea, since we hope to mostly be dealing with poles, of order m, it is convenient to to find residues in terms, we'll say in terms of the, I guess we should say in terms of the algebraic expression showing up in the principal part of f of z. Okay, which is what we've been doing. I mean, our usual way of doing that is we literally, we just write out the Lorentz series and identify the 1 over z minus z naught term, and that's our residue. But if we know that the thing is a pole of some order, maybe there's like a little quick shorthand way of doing this. So to that end, we have the following theorem. So an isolated singular point of f of z. So we'll call this isolated singular point z naught. So an isolated singular point z naught of f of z is a pole of order n if and only if f of z can be rewritten in the form f of z is equal to phi of z over z minus z naught to the m, where phi of z is analytic and non-zero at z naught. Okay. In this case, moreover, the residue at z equals z naught of f of z can be computed by just plugging in z naught into phi if m is equal to 1, and if m is general, the residue at z equals z naught of f of z is the m minus first derivative of phi evaluated at z naught over m minus 1 factorial. Okay. Okay. Notice the relationship between this and what I wrote previously. Let me find my characterization, right, where I said if f has a pole of order m, if I multiply this f by z minus z naught to the m, I get this expression. What is this thing, this power series here? This is phi of z. Right. So in that previous thing that I wrote, this is phi of z, which of course means that f of z is phi of z over z minus z naught to the m. So this actually serves kind of as the proof for this theorem, right? This is exactly what it is that's going on here. Okay, there's a little bit more details need to be filled in, but I'm not gonna bother with that. So how can I actually use this to compute some residues for some functions? So let's see how useful this is. So here's the first example. So let f of z be like z plus 1 over z squared plus 9. Okay. Okay, so z squared plus 9 here. That's that means that I have isolated singular point, for instance, at z equals 3i. So z equals 3i is an isolated singular point. Okay. All right. How can I rewrite this in some form that looks like this? Well, I can actually factor this bottom. Alright, this bottom quadratic fully factors. This is z plus 3i times z minus 3i. Okay, so this is 1 over z minus 3i times z plus 1 over z plus 3i. And so I can rewrite this as phi of z over z minus 3I, where phi of z is this thing. Okay. Now, since I can write it like this, this is a pole of order, since phi of z is analytic, so this is analytic non-zero. Both of those are required. Analytic at non-zero at z naught equals 3I, right? i.e., by this theorem that I have written here, if I can write it in this form, where here m is 1, right? Where phi is analytic and non-zero, this can occur if and only if an isolated singular point of f is a pole of order m. In this case, it would be pole of order 1, so a simple pole. Okay, so this means that z naught equals 3I is a simple pole of f. This is a simple pole of f of z, and if I wanted to compute the residue at 3I of f, this can be computed by my theorem. Since this is a simple pole, I can literally just plug this into phi. Right, so this is phi of 3I, which is 3I plus 1 over 3I plus 3I. Okay. What is this? Well, this is 3I plus 1 over 6I, which I can rewrite as 3 minus I over 6 after I do that division. Okay, multiplying by like minus I over minus I, right? Similarly, the residue at minus 3I of f of z is phi of minus 3I, where the phi in question is different. So this phi is, instead of being z plus 1 over z plus 3I, it would be z plus 1 over z minus 3I. So this phi is different. Maybe I'll hear squiggle phi. So this is 3 plus I over 6 is the residue. Okay. All right. So this gives us a quick way of computing the residue like this. We didn't even need to do any more computation with Lorentz series expansions. You don't have to expand anything or do too many algebra tricks. Let's do another example, and then I think we'll be done for today. So my next example is let's let f of z be z cubed plus 2z over z minus I cubed. Okay. Well, then I can think of this as phi of z over z minus I cubed, right, with phi of z equal to just that numerator. That's analytic and non-zero at I. So analytic and phi of I is I cubed plus 2I, which is actually just I. Right, it's minus I plus 2I, so it's just I. So that's non-zero. So it's analytic and non-zero, so what does this mean? So f has a pole of order m equals 3 at z naught equals I. Okay. And then the residue of f at z naught equals, z equals I is by this formula. Since here m is 3, this is the second derivative of phi evaluated at the z naught in question over m minus 1 factorial. So this is phi double prime evaluated at I over 2 factorial. So this is the first derivative of phi is 3z squared plus 2. The second derivative of phi is 6z. So this is 6i over 2, or 3i. So again, very quick way of finding the residue here. Okay. All right. Okay. So next, all that is left to do is show how zeros of functions relate to poles, which we will do. And once we have talked about that, basically we're going to be moving on quickly to applications of residues. And the main application that we want to discuss is applications of residue, of the residue theorem to computing improper integrals of real valued functions that maybe are otherwise kind of intractable. Okay, so this is going to be our ultimate application of this stuff. All right, and then that's basically all the course material. Okay, so I will see you all tomorrow.